All right, hello everybody, and welcome to day 2 of our Unit 7, our day 2 of Calculus BC. And this is extending, honestly, yesterday's lesson on integration by parts. Okay, so I'm actually going to show you two special types of integration by parts, scenarios that we run across. Before I do that, though, I wanted to talk about this fun little integration. All right, look, so if I were to do do this integration here, I got an algebraic term, a polynomial times a natural log. Okay, two things being multiplied together. So one of them is u and one of them is dv. Remember Liate. And as we go down the list, the first thing we come across is that L, which stands for log. So this is going to end up being my u. But let me stop right there. Just save you a couple steps here. If you try to do this problem where this entire quantity is u, that's fine. It's just that du is going to end up being 1 over 2 plus x squared times, by chain rule, 2x. And it comes to a type of integration that we don't know how to do yet, that we're going to learn later on throughout this unit. What simplifies this process, and just a little lesson to this, is you can do a u substitution before you do separation by parts. So for instance, like at the very beginning here, what if I let u be 2 plus x squared, the inside of ln? Then du would be 2x dx, and we can have 1/2 du be x dx. So x dx can simplify this down by a power of 1 and dx, and a 1/2 can come out. So what I'm left with is 1/2. One of the x's substitutes out, so I got x squared, and then the ln of u u du. Okay. And remember, if I'm doing u substitution, everything needs to be in terms of u, so I can actually rewrite this x squared as 2 plus x, or I'm sorry, this x squared as u minus 2. So I can really say this is the integral of u minus 2 ln of u du. Okay? And I think doing this u substitution will make doing integration of parts a lot easier. Again, you didn't have to, but when we came down to the integration without doing it, it's not something we know how to do yet. But we still have two things multiplied together. We still have a function, polynomial times a natural log. So I can still do Liate. And since I've already used the letter u here, I'm going to do w and v instead of uv. But I'm going to say w is ln of u. It's ugly, sorry. And that makes dw 1 over u. I'm going to make dv that ln of, I did it again. I'm going to make it that u minus 2 du. So then if I integrate that, that's simply 1/2 u squared minus 2u. Okay. All right, now I'm doing a little zigzag here to keep me on track. So I'm going to do wv minus the integration of v dw. Okay, and this is just a lesson from yesterday. Okay. So that becomes, and I apologize, and I don't want you to forget about this. Don't forget about your 1/2, because I almost always do. So anyway, we got 1/2, and then I'll multiply everything out. That's wv, so I'm going to say 1/2 u squared minus 2u times the ln of u minus the integration of v dw. So that's going to be 1/2 u squared minus 2u, all multiplied by 1 over u du. Okay. And I forgot the du right here, so. Okie dokie then. Before we integrate, let's simplify down inside the integral here. So we got 1/2. I'm just going to rewrite everything again. U squared minus 2u ln of u minus, simplifying down that, I'm just going to distribute the 1 over u through, and it's going to be 1/2 u minus, and that's just 2 du. And then the rest of this is pretty straightforward. You just integrate it, got your answer. Excuse me. So I got 1/2 on the outside. 1/2 u squared minus 2u ln of u minus the, and in parentheses, the integration of 1/2 u would end up being 1/4 u squared if I add 1 and divide, minus 2u plus c. Now that's a mess, but don't forget that this was in terms of x at the beginning, and u was equal to ln of 2 plus x. Oh, I'm sorry, not ln. It was just 2 plus x squared. I apologize. 2 plus x squared. All right, so we're going to plug that back in for u, and then we're done with this problem. So it's going to be 1/2, in parentheses, 1/2, instead of u, it's 2 plus x squared, minus 2 times u, or 2 plus x squared. And then all of that, remember, all of this is being multiplied by the ln of u, or 2 plus x squared. And then minus 1/4, instead of u, it's 2 plus x squared, minus 2 times u, or 2 plus x squared, and then plus c. That was a big boy problem, big boy and girl problem there. So we had to plug u back in, and this is my final answer. I wouldn't try to simplify it any more than that. So integration by parts can get fun sometimes, but anyway. Let's look at some more problems. All right, pause the video, finish up the last problem if you need to, but let's talk about this one. This is another special type of integration by part. Okay, this is a more common one than the one I just showed you. This pops up all the time. It's when you have two things multiplied together, and more specifically, it's when you have an exponential multiplied by a common trig. If you have that, there is a pattern that happens with this. Okay, now let's just go through the steps and you'll see the pattern. You'll see the issue you run into. So let's start off by doing what our u is and what our dv is. Now remember Liate. Okay, go down the list. There's no logs. There's no inverse trig. There's no algebraic expression. First thing we run across is trig. So I'm going to let u be cosine of x and dv be e to the x dx. So then du, the derivative of cosine, is negative sine of x dx. And v, the integration of e to the x, is just e to the x. Okay. So we should be pretty good at integration by parts now. Let's think about how this works. And for the pattern of this problem, I want you to rewrite the beginning of the problem as we go. You'll see why in a second. So what this is equal to is uv, or simply put, e to the x cosine of x, minus the integration of v dv. So this times this. And because there's a negative, I'm going to go ahead and take the negative out, make this positive. So I'm left with e to the x sine of x dx. Okay. Now, here's the issue that we run into. Okay. If I want to integrate this, well, unfortunately, the only way to integrate that, if you go down your list, you try to use substitution, try everything, the only thing to do is that we have an exponential times a trig again. The only thing we can do is integration by parts. So within this problem, I'm going to have to pretty much do it over again. I'm going to have to do this as an integration by parts. So we're going to have to do, it's like Inception, integration by parts within integration by parts. So let's do that off to the side here. I'm going to let u be sine of x, or like I did earlier. I'm going to let du be cosine of x dx. I'm going to let vd be e to the x dx, and I'm going to let v be e to the x. So let's rewrite this bad boy. We got the integration e to the x cosine of x dx equals e to the x cosine of x plus, and I'm going to write this in, I'm going to write out what this is equal to now. Okay, this is equal to, based off of the integration by parts, it's plus uv, so e to the x sine of x, uv, minus the integration of v du. That's e to the x times cosine of x dx. E to the x cosine of x dx. Okay? All righty, well, then you get down to it, and here's the issue. When I get down to taking the integral of this, so like I said, what I did in blue here was the second integration by parts, but what's the issue? Well, look what I got to take the integral of. It's just going to, it's an exponential times a trig. I'm going to have to do integration by parts again. But if I do that again, I'm just going to end up right here. It keeps rotating itself over and over again. I mean, look at what I'm given right here. This integral is the same exact integral that I started with. So if I keep going, it's just going to keep expanding it farther and farther again. But there's a simple fix to this. And it only required us to do integration by parts twice, because once I have the same thing over here, well, what would happen is if I shoot that over to this side? They're the same thing, right? So what if I decided to, instead of minusing, what if I added this to the other side, to almost like I'm canceling it out? So that goes away, and I add it over here. Well, if I have one integral of e to the x cosine of x plus one integral of e to the x cosine of x, what does that equal? Two integrals e to the x cosine of x dx. And with this gone on the right side, what I'm left with is e to the x cosine of x plus e to the x sine of x. What's left over? So then, simply put, all I have to do, because remember, I'm trying to figure out what the integral of this is. All I got to do is divide both sides by 2. And that's it. Divide both sides by 2. And I'm left with the integral from the very beginning, the one I'm trying to solve for. And all the integration has happened. So this is 1/2 ex cosine of x plus ex sine of x. So that is a common thing. So if you ever run across the integration of an exponential times a common trig, so cosine or sine, or even, well, actually just cosine or sine, you're going to have to pretty much follow this process. Do integration by parts twice. Make sure you have the expression over here on the left, because you're going to end up combining like terms, and you'll get your answer. Not a bad pattern once you recognize it. Okay, I got 3 more, and hopefully we'll get through them all, but at least I want to get through these next 2, which is practicing the next pattern. So before, I don't really have a name for that, but it happens when you have exponential times a common trig. This is called tabular method, because you can rewrite this as a table. And this is really, really helpful, because if you didn't write this as a table, you would end up having to do integration by parts like 5 or 6 times. It's ridiculous. Here's the cool thing. Okay, this is just a simpler way to set up the problem. This happens whenever you have a polynomial, okay, whenever u is a polynomial, when it's combined with either trig or exponential. So I'm going to make a note of that over here. So this is really helpful whenever u is a polynomial, whenever you make u a polynomial. And dv is either, I'm going to say, a trig function like sine or cosine, or an exponential. So in this case, we have a polynomial times a trig. So it's especially helpful with a polynomial of a high degree. Otherwise, you're doing integration by parts multiple times. So this is how you set it up. we're pretty much going to just keep track of all of our integration by parts in a chart. This is how I want you to do it. I want to keep track of all of your u's here. Okay? And when I say that, you're going to be, as you go down the chart, you're going to be figuring out what your DU's are. Okay, so like, yeah. Here, you're going to keep track of your DVs. And as you go down the chart, you're going to be integrating it, right? Integrating versus taking the derivative. Okay? And over here, I want you to keep track of your signs. Okay? Whenever you do integration by parts, it's always UV minus the integration of V du. The signs on the chart right here is keeping track of this minus. That minus is constantly changing our signs when we do integration by parts. It's a really simple process. All you do is you start off with your u being x to the fourth. And you're going to keep taking du all the way until you get down to 0, because that's what would happen if you did integration by parts. This will be 3x squared. This will be 6x, then 6. Oh, wait, no, I did terrible math there. God, that was terrible derivative. I'm so sorry. I don't know what I'm thinking. I can't take the derivative and save my life today. We'll start off with x to the fourth. So that's 4x cubed, then 12x squared, and then 24x, 24, and then 0. Here's the thing. If you did this by integration by parts, this is how many times you'd have to do integration by parts because of how the problem is set up. So this just simplifies that process. All right, then you keep track of all your DVs. So you start off with the first one, sine of 2x, and you're going to keep integrating. Okay? And you can pause the video if you want. I'm going to go through these integrations pretty quick, but integration of sine of 2x is negative 1/2 cosine of 2x. Remember that the 2x really just comes out as a 1/2. The integration of sine is negative cosine. All right, taking the 2x again out as a 1/2, that's negative 1/4 sine of 2x. Integration of that is 1/8 cosine of 2x. Again, pause the video and try these integrations out. Integration of that is positive, 1/16 sine of 2x. And the integration of that, all the way down to that last term, is negative 1/32 cosine of 2x. So all I did was make a chart with all my u's and all my dv's. And I just went down the chart from the first polynomial all the way down to 0. Again, that's how it's set up whenever you're dealing with polynomials times a trig. And how the signs work, it's super simple. It always starts off positive and then just alternates all the way down. Negative, positive, negative, and that's it. And you're going to love this. The answer is simple. It's just the product of the diagonals, and that's it. I'm going to use a highlighter to show this. It's super duper simple. If you can set up the chart, you got the answer right away. Use a highlighter. Do yellow. Okay. It's this product, so those three. This product, so those three. This product, so those three. 24x, 1/16, and the negative. And then my last term is the 24, this term, and then the last sign would have been a positive. And that's it. Okay, so let's write this out. I love tabular because it really simplifies it down. I guess okay, so it's x to the fourth, negative 1/2 cosine 2x. So that's going to end up being negative x to the fourth, 1/2 cosine of 2x. That's the first one. The second diagonal is the 4x cubed times the negative 1/4 sine of 2x times the negative. Negative times the negative makes it positive, and the 1/4 and the 4 just become 1. So really what I'm left with is x cubed sine of 2x. The next diagonal is 12 1/8 positive. So that's, I'm just going to keep it unsimplified for the sake of simplicity here. 12 over 8. 12 over 8, and then the x squared cosine of 2x. The next diagonal is 24 1/16 negative, so that's actually going to be minus 24 over 16. We have an x, we have a sine of 2x, and that's it. And the last diagonal is 24 times negative 1 over 32, and then there's a positive down here if I keep going. So that ends up being positive 24 times negative, so that's going to be minus 24 over 32, which does reduce down to 3/4, cosine of 2x, and don't forget your plus c. So look at all of this would have been additional integration by parts if I didn't do a tabular method. But it's so simple once you set up your table, I promise you. If you can start off with your u and your dv and take the correct derivatives all the way down to 0, and then the correct integrals with the correct signs, positive, negative, positive, negative, positive, negative, positive, then just the answer is the product of the diagonals. Tabular method is so awesome. Let's do one more with tabular method. We got t cubed e to the t. Now look, it's a polynomial times an exponential. Again, if you have a polynomial times an exponential, that's tabular method. That, or if you had a polynomial times a trig, that is tabular. The other thing we learned today is if you have an exponential times a trig. That was that special rule that we learned when we had to combine like terms. So those are the three, I guess, things that we learned today. This one's, you'll love this one. This is my favorite. Okay, this is u, this is dv, and this is my sign, positive, negative. So look, my u starts off as t cubed. So then it's going to go all the way down. 3t squared, 6t, 6, and then 0. I love dv. dv is e to the t. What's the integral of e to the t? E to the t. And then e to the t. This is like my favorite. I love it. I love it whenever it's e to the t, because the integration is always the same, so it's super duper easy. Okay. And the signs go positive, negative, 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 positive, negative, positive, negative, positive, negative. Okay. Now, this prevents us from having to do integration by parts so many times, because the answer is just, I'm going to circle it this time. That diagonal, that diagonal, that diagonal, and 6e and negative, that diagonal. So my final answer is, if I multiply those together, I have a t cubed et, and then and the second diagonal, it's a negative, because we have positive, positive, negative, so that's a minus 3t squared e to the t. The third diagonal, it's positive, 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 so this is just plus, and that's 6t e to the t, and then minus, because it's positive, positive, negative, 6e to the t plus c. Tabular made that process so. Otherwise, if we did integration of parts, we were just taking forever on that. I love it. I love it. All right, 24 minutes. Shoot, I can do the last one. I got that one. Oh, yeah, baby. I'm finishing this lesson. Let's go. All right. Pause it. Try it on your own. See if you can do it. Can you recognize the type of problem that we have here? This is a trig times an exponential. OU sub, no quick simplifying, no easy integral. Trig times exponential. That's the type of problem that we have whenever we're going to have to combine like terms. Okay, so keep that in mind, like that first example we did. So Leate says that I'm going to do trig as my u. So I'm going to do u equals sine of x, and du is cosine of x dx. And dv is equal to 5 to the x, and v is equal to, the integration of 5 to the x is 5 to the x. But don't forget, because it's something other than e, we also have 1 over, integration, sorry. 1 over the ln of 5. Don't forget about that. Okie dokie, so we're going to do integration by parts, a little v there. And remember, my suggestion for these is to rewrite the problem, because we're going to end up having to repeat ourselves so much rather than combine like terms. So this is equal to uv, so that's sine of x, times, I guess, 1 over ln of 5 to the x. There's uv. Minus the integration of v du. Now, because 1 over ln of 5 is a constant, I'm going to go ahead and bring that out. If I can bring out a constant at the beginning, I'd love to do that. And I'm left with cosine of x times phi to the x dx. Okay, now the reason I brought the 1 over ln of 5 out in the first place, too, is because now I'm going to have to integrate this. And if you notice, it's pretty dang similar to what I started with. And if you notice, when I integrate it again, I'm going to end back where I started. That's what happens with exponentials and trigs being integrated together. So let's write it out. Integration sine of x 5x dx is equal to, so I'm going to rewrite this first part here. That's sine 1 over ln of 5 to the x. Okay. Minus, I got ln of 5 on the outside, and I'm going to do integration by parts again with this right here. I'm going to try to, what am I going to squeeze this in at? Squeeze it in above it here, just for sake of space. I'll say that u is cosine of x, du is negative sine of x, dv is 5 to the x, and I'm going to squeeze v right here. V is equal to 1 over ln of 5 to the x. Oh my goodness gracious. 5 to the x dx, or just 5 to the x, sorry. Yikes. Okay. Well, anyway, uv, if I were to do uv, so cosine of x times ln of 5 to the x, that would be, I'll just write it this way, 1 over ln of 5 to the x, cosine of x, okay, plus, and then the integration of v du. So here's du, here's v. I'm going to go ahead and bring the 1 over ln of 5 on the outside again, and I'm left with the integration of v du. That would be, I already missed saying this, I'm sorry. I made this a plus here because I'm taking out the negative sign. So that makes it not minus, but plus 1 over ln of 5. I apologize for that. But the reason I'm doing all that is because I'll be left with sine of x, 5 to the x dx. That looks like a mess, but the integration I'm left with is the same integration I started with. So before I can shoot that over, though, I'm going to have to distribute this 1 over ln of 5. I got to get rid of all the parentheses, and then I can combine like terms. So I got sine of 1 over ln of 5 to the x. If I distribute this through, this is going to end up being 1 over ln of 5 squared, 5 to the x, cosine of x, plus 1 over ln of 5 quantity squared, and then the integral of sine of x, 5 to the x dx. Now, everything is distributed, okay? Everything is distributed. So if I want to get this answer by itself, instead of adding, I'm going to subtract 1 over ln of 5 squared integration sine of x 5 to the x dx. That cancels this out, and if I were to subtract that over here, 1 over ln of 5 quantity squared integration sine of x 5 to the x dx. If I add those together, that if I combine, it's like one of these integrals minus 1 over ln of 5 squared of those integrals. I'm going to be left with, combining like terms, 1 minus 1 over ln of 5 squared. Integrals of sine of x 5 to the x dx. I just combined like terms there. And for sake of time, I'm running over, I'm sorry, this is equal to the sine of 1 over ln of 5, 5 to the x, minus 1 over ln of 5 quantity squared, 5 to the x cosine of x. That's what's left over. And now the only way to get the final answer, which is the integration of this, you're going to divide both sides by 1 minus 1 over ln of 5 quantity squared. So, my final answer, and I'm going to leave this as unsimplified as I possibly can, is equal to all of this, so sine 1 over ln of 5, 5 to the x minus 1 over ln of 5 squared, 5 to the x cosine of x. I'm going to leave all that divided by that left side, which was 1 minus 1 over ln of 5 squared. Woo-wee doggy. Now, that was a hard one. That was a good one. Okay? All right. So we learned tabular method, and we learned this special little case here. All right? Now, for homework, so we got through the entire lesson, which is good. For homework, if you want to try a few of these problems, try this page. Try these problems. There's some tabular method in there. There's some of the problems like we just did. And we will obviously reconvene and talk about this when I get back. Okay, so thank y'all for watching the video, and sorry I'm not in class for this video, but we will summarize it soon. All right, I'm done.